So let's continue to the second type of motion in 2D for rigid body. That's Rafa. So let's focus that for now, and that is the major focus for the remaining of today's class, Rafa motion. So let's talk about rotation about a fixed axis. And again, that is Rafa. And as I make an analogy in the previous video, if we're talking about the tennis, when we talk about Rafa, it means Rafael Nadal, a Spanish tennis player that is ranking very high now and also very famous. And I'm a supporter of, I'm a fan of Rafael Nadal. But in this class, we talk about Rafa, it means rotation about a fixed axis. But the analogy here, when we talk about the tennis, we need a tennis racket. If we were talking about the Rafa in this class, we need to draw a Rafa stick. Keep that in mind. So let me emphasize again one thing that you have to remember for the rotation about the fixed axis is the Rafa stick. Just like in the tennis, if you go to court, if you don't print the racket, then deal. Nothing you can play. So let's talk about the Rafa stick for here. So let me draw a body in rotations about a fixed axis. So let that point here, and I call that point A, is a fixed axis, point A. So its rotation about a point, in this case point A, and about the axis perpendicular to our screen, and that we say this body AB is Rafa. Or I can say that when you, about steering wheel, when you drive a car, when you turn left and right, that basically Rafa motion of the steering wheel. So with that, we can have point A and point B. When it rotation, let me assume this body in clockwise rotation. So at certain points, certain time later, they move to another position, and that B become B apostrophe. And you see that there? And because the axis go through A is fixed, so A is not moving. And that's why we say fixed axis go through A, perpendicular to your screen. And from that, let me define a few information here. So the displacement for that instant, we call it delta S. And that displacement create a displacement in the angles, the central angle here. And like I say, we assume that rotation in clockwise. So I call that d theta, a change in the angles. And with that, we can have the B, and you can see it like rotation on a curve motion there. And when the point B in the curve motion, the velocity of that point will be tangential to the path. What does that mean? At that given point, it will be perpendicular to the radius of that body. Go through A, in the center in here. So that point B move to B apostrophe. I call that a velocity VB, tangent to the path, perpendicular to the radius. That's what we already know. Okay, and with that, we can make some transformation with the physics and math. So let you see if the displacement, the point B, move to B apostrophe, then I can have delta S, the change in position over a time, equal to ds is equal to r delta theta, the change in the angles at point A over delta t. So the delta S equal to R delta theta. If you don't know, oh, what is that? Then if you recall the quiz, the problem number 6 in the quiz, practical kinematics 1 quiz, you have the angle theta equal to 60 degrees, and the radius, you can find out the displacement. Recall that. If not, I suggest you to go to problem 4, practical kinematics 1. In the worksheet problem, you can review that relationship. So with that, let me move on to here. So delta S, delta T, it means that we can have the ds over dt. And then equal to R d theta, even a smaller time and smaller angles and smaller change in displacement. So we have that. And let me set d theta over dt, the change in the angles in a unit of time. We call that is omega. And this is, we box this equation. So the change in the angle over time, the first derivative of the angle change at the point that body rotate about over time, with regard to time, we call it omega. And this omega, if you recall, we call that in physics, it will be angular velocity. And velocity. Okay, and what is the units of this angular velocity? The units are radian per second. Radians per second. That is the unit of the angular velocity omega. So how can I solve it in here? And you can see omega equal to d theta over dt. So if the body rotation in this case is clockwise motion, then the omega also clockwise motion. So let me show that here. Omega, angular velocity, will be clockwise motion if the body rotates, the Rafa body rotates in clockwise motion. So it will be consistent with the motion of the motion with the angular velocity. And with that, as you can see now, if you recall, ds over dt, it actually the change in the displacement of coordinate over time, it will be equal to the velocity. So compared to that, v equal to ds over dt, and in the equation previously here, it equal to r d theta over dt, and the d theta over dt we call it omega. Then we have the equation there is velocity at a given point equal to the angular velocity of the body times the radius of the bodies. So let's box the next important equation there. So v equal to omega r. So as you can see, v, velocity of point B, and omega have relationship. What is the radius? The radius basically the position vector that I write down here. Position vector from A to B. So to B from A. That is the radius. So let's talk a little bit about the characteristic of the velocity in Rafa motion. So let's continue about the velocity in Rafa motion. Velocity in Rafa motion. So just rewrite, and you can see the omega and radius have relationship with the velocity at a point. So let me rewrite here. If I have point B as shown in the Rafa stick there, it equal to, if it in scalar, so I can write it omega body, the angular velocity of that body times the position vector or the distance from A to B. If we talk about scalar, here is scalar. And now if we work on the vector, then we can have VB vector, velocity of point B, possible Fi slope in that rafa stick here. Then the VB in this case, it will be equal to omega body vector cross product, not dot, position vector 2B from A, and that is a vector form. Vector form. And this equation, these two equations, apply for rafa only. Keep that in mind. So how about the other two motion? Translation, let's go back to our practical kinematics. How about GPM, general plane motion? We are going to talk in the next lesson. So for now, these two equations applied for rafa motion, rotation about the fixed axis. So as you can see, very important point, and I will pull out in the next video, but let's take a few note here. The VB, basically we have to specify a point for the velocity, and that we call it a point property. So velocity for a rigid body, we need, especially rafa and GPM, you need to specify which point when we talk about the velocity. But now if the omega is about the body property, so you don't have to specify any point for the omega. It applies for the whole body. What does that mean? Any point on that body will have the same omega. That's why they call it body properties. Any point on that body don't necessarily to have the same velocity. That's why point properties. Only that point may have that velocity. The other point on the same body have different properties. That's why we need to emphasize the point property and body property in the rigid body kinematics class. In the next video, I will show that one PDF file in this lesson that you refer to. So a few more characteristics before we close for this video and move on to the acceleration for the rafa. So the first note that I want to see, the velocity at a point is always perpendicular to the radius. Okay, so velocity perpendicular to the radius, as you can see in there. Okay, because it's tangent to the path. And then the second note is velocity v consistent with or same direction of omega. Directions of omega. So what does that mean? Omega, if the body in this rafa stick, as you can see, if omega is clockwise, then the VB, you see that there? VB, velocity VB, is the same consistent. It goes to the right? If omega counterclockwise, then velocity B go to the left. So that we're talking about the consistent in terms of direction between the angular velocity and velocity of a point. So bottom line, if we know the direction of one point on the rafa body, we can know the direction of the angular velocity, and vice versa. If we know the angular velocity clockwise or counterclockwise, we can know the direction of the velocity of any point on that body. So with that, we stop here for the velocity of rafa, and the next video we will move on with the finish with the rafa stick for the acceleration part.